Thanks a lot for the introduction. Yeah, so I'm going to talk about efficient deep learning on edge AI accelerators, right? So I prepared a talk where we will go through some like general concepts on AI for edge devices, and then we'll talk about some hardware acceleration concept for like speeding up this AI workloads for the edge. And then we'll do some deep dive on how to efficiently utilize these accelerators and some future trends. Please feel free to like ask questions, make comments. It is going to be somewhat like general overview of the concepts, and then we'll do some deep dive on some of the recent works, right? So yeah, let's get started with the AI on edge devices. So why we need them and what is actually edge device, right? So when we talk about edge, we are really like contrasting it against a data center, right? So when you consider this sort of like distributed computing environment, we have a cloud and data center that is sitting and like doing all the expensive computations, and there's the like the leaf nodes in this network where you have your mobile phones, IoT devices, smart home, et cetera. And conventionally, these edge devices are more or less doing like a very lightweight work and collecting data and sending it to the data center and cloud to do the processing. But we are seeing a trend where the AI workloads are being pushed to the edge, right? And just put together some examples of this. There's actually many more, but today on your mobile phone, for example, you could do things like this, right? So you could take a picture and tell your phone that remove people in the background, right? And then it can detect and then remove them. So when you actually consider what's happening here, there's actually multiple levels of AI, right? So there's like speech processing that understands what you said, and then there is multiple levels of computer vision happening. It detects that there's actually multiple people, some of them in the background, some of them in the foreground, and then removes and replaces with the like the correct pixels. And like some other examples, face deblurring, right? So you take a picture, it's blurred, and then you can deblur it. Like conventionally, a lot of these, use more traditional computer vision algorithms, but today most of these things are done using AI. And like another example here, let's say you have a ticket that's written in some language, and then you can actually live translate it like real time and detect the text, replace it with the other language. Or here in the middle, let's say autonomous driving, we have to detect other cars, pedestrians, and the signs and all that, right? So all this AI is needed for the edge devices. But the question is, why do we have to run them on the edge device, right? So you could actually collect this data, send it over to the cloud or the data center, run it there, and collect the results back. But yeah, that could be possible for some of the use cases, but for some of them, it's not ideal, right? Because imagine you may want to have your privacy, right? So you take a picture and you don't want to send that picture to the cloud for the processing. You want to keep it local, or you want it always available, right? So maybe you don't have connection and you have to do that like processing locally. So the availability is another important thing, and the biggest one is obviously the performance and power, right? So you want you want to avoid this costly communication, and you want it to be really fast. Imagine like self-driving car, detecting pedestrians or other cars. It has to be like you don't have the luxury to send this data over over communication channels and receiving it back, right? So it has to be super low latency. So that is why, like, that's the big motivation for specific hardware for AI workloads, right? And we are talking about the hardware accelerators. And I just put together like some motivational data for that. So this is from ISCA paper, right? So it is comparing CPU, GPU, and the TPU, right? TPU is the the tensor processing unit. This is the machine learning accelerator. CPU, GPU, I'm sure everyone is familiar with it, right? So I mean, the GPUs are probably one of the factors that the AI got so big in the recent years, right? Because it can run the backprop and the whole training in parallel, fast ways. But then this may not be sufficient for some of the use cases that we are seeing. And in this data, what we are showing here is the performance per watt, which means like how much performance that you gain per energy that you burn, right? So for some of the cases, if you put more and more resources, you can actually get speed ups and like better performance, but at the same time you're consuming more and more energy, and you become like energy limited. So so here the real efficiency metric is performance per power, and this is comparing GPU and TPU to CPU platforms. So without going into all the details, what we are seeing here is, I think the TPU prime is the latest generation, right? So if you compare TPU to CPU or GPU, we are seeing a huge improvements, like in the orders of, somewhere between like 40 to almost 200. So this is like a big game changer, right? So if you have this custom hardware, it's not like you're gaining few percentages, but you're gaining like multiple orders of magnitude improvements. This enables a lot of like real-time AI that wasn't like possible using general purpose cores. Right, so this is one of the biggest factors in investing in this sort of hardware for AI. Just another motivational data. This is from our recent work. This is targeting a mobile SoC. It's Tensor SoC from Pixel 6 phone. And within this system on chip, there's actually CPU, GPU, and the TPU. Right? And then this graph that we are seeing, a neural network, when it run on CPU, it's around here. And if you take it, then just run it on TPU, you get this much benefit, right? So this could be the difference between real time and non-real time, right? So you're actually here seeing like there's few more data points on the top. I'm not going to talk about them yet, but we could actually do even better than this, right? So we'll talk about that, how we can achieve it, right? I mean, not surprisingly, after seeing all that data, right? So we see that all recent modern like system on chips for edge devices come with some special machine learning engines, right? So the Google's Tensor, Apple's like A14, like all other SoCs as well. You would see that there's special cores for machine learning, right? And even more, like this is some data available online. This is the AI chip landscape. It's actually not even very recent. I think this is a few years old, but still there's actually so many companies and like so many efforts in this market, right? Like all the tech giants are building their own custom hardware. There is like IC vendors and IP design services that are trying to enable all this hardware AI effort. There's so many startups in the worldwide and even in China, like there's so many of them. And there is also software effort that is trying to enable all this new hardware technologies and new benchmark coming up, right? So, I mean, the bottom line is that this is really happening. There's a like big need for this, and there are also alternative ways to achieve this hardware acceleration for AI. And yeah, so we are going to talk about how deep, like we will do a deep dive on some of these systems and see how we can efficiently utilize them for deep learning. Yeah, so basically, I just wanted to mention the challenges of this as well, right? From a very theoretical standpoint, right? I'm not sure if you're familiar with the roofline plots, but in summary, what this is that we are plotting a hardware system, in this case, a TPU, tensor processing unit, and then we are showing its sort of performance, which is teraops per second, like the throughput, against the operational intensity, which is the operations per weight byte. So what this means, operations per weight byte, is that whenever you fetch a parameter of a neural network, you're doing several operations with that. So if you do more and more operations, that means you're amortizing that fetch from the memory, right? So then it becomes more and more compute intensive. And if you're doing only few operations after fetching that parameter, that means you're doing less computation and you need more and more memory bandwidth. But memory bandwidth is limited, computation is limited. When you plot this chart, this blue line becomes the machine's roof line. So you can't go above this line. And your neural network has also characteristics in terms of computation and parameters or weights. So basically, they land up in different parts in the graph. Now, this point is the break point where if you're towards the left, you're memory bound. If you're towards the right, you're compute bound. But I just wanted to highlight that this is very limited set of neural networks, some LSTM types, MLP types, and CNN types. But the bottom line here is that we do see there is no common trend, right? For example, CNNs are on the towards the right, they are compute bound, and the other types are on the left, they are memory bound or heavily memory bound, for example. So there is no a balanced machine that can be efficient for all the networks. So this is one of the biggest challenges, right? And why this is happening, actually more insight into this one is, it's just a very quick demonstration, but you would understand that for different types of networks, there is actually different type of trade-offs that make it challenging. For example, this one is a convolutional layer. Just the theoretical demonstration of that, right? So you have an input tensor, you have a kernel or parameter or weights, however you want to call them, and you're generating an output. So if you actually calculate the number of operations that this convolution is doing and the number of parameters it has, you would end up this ops per parameter number as YO times XO. And if you do the same, for example, for the fully connected layer, these are much different numbers. So this number is showing us for every parameter that we fetch, how much, how many operations that we are performing. So this number, if this number is high, that means we are tolerating that parameter fetch and becomes compute intensive. But for this one, there's actually a single, we are doing one multiply accumulate for every parameter. That means we need to, we need a huge memory bandwidth to sustain this computation. So even this, right? So if your network has a lot of convolution, it will become compute intensive. If your network has a lot of fully connected, it will become memory intensive. And this is true for other types of operators in the neural network. And that's why there's no one size fits all, right? So there's it is very challenging to design a balanced machine that can be efficient for all types of networks. Yeah. So then the question is, how can we achieve efficiency? How can we use these accelerators so that we can achieve high efficiency in terms of energy, performance, and achieve real-time AI? Right. So I'm going to highlight few areas for utilizing efficiently. Right. So, and then we'll talk about how, what is a systematic approach that that can utilize those components better, right? So one of the concepts is the data reuse, and why this is important, right? So this is from the Iris paper. This is one of the earlier AI accelerators, published in 2017. It is demonstrating a relatively simplistic architecture where we have an external DRAM and some internal global buffer and a set of PEs. And in each PE, there is a register file and ALU, right? And then we do the multiply accumulate, the core of the computation in each ALU. So we need to fetch the data all the way to here so that we can do the computation. And they compare here the energy of each operation, like just doing the compute, reading from register file, moving data over the network on chip between the processing elements, buffer, and the DRAM. And you would see that accessing the DRAM is almost 200x cost of doing a computation. So it is very important to have a good data reuse, where we minimize the number of DRAM accesses and we maximize the data reuse. So our data fits in the global buffer or fits in local PE memories, and then we do computations effectively from there. So one of the goals is to minimize such external accesses, which are extremely costly. Right, so another important concept is the data parallelism. In this case, SIMD parallelism. What is SIMD? SIMD is single instruction, multiple data. You can think of them as like a vector processing, right? So a lot of the hardware AI accelerators utilize SIMD because when you think of the core of the neural network computations, we are processing extremely large tensors that are generally, that have shapes which are aligned to the hardware dimensions. So, for example, if you may have a tensor where the innermost dimension is large enough that it can be processed in parallel by multiple sort of multiply accumulate units, right? So another very important aspect is to have good shapes that can utilize these wide vector engines, right? So that we can have good utilization and efficiency. This is another key concept. The third concept that I want to mention is the data flow, or the general data path of your accelerator. I pulled this from, again, the ISCA paper from the TPU. This is the overview of that architecture. So without going into full details, I just wanted to highlight the core of this architecture, which is this matrix multiply unit. So it is built from a systolic array, and the systolic array's data flow is quite unique, right? So you need to have a very good mapping of your tensors and your computation into this matrix multiply unit, so that it can reach high utilizations, right? If your matrix is not well shaped, for example, it might be very narrow, it might be super wide, but not enough rows in the matrix, things like that. It may lead to underutilization. And this is just one example, right? So systolic array is one way to put together those multiply accumulate units. You might have different type of architectures. So the bottom line here is that you need to be aware of the underlying architecture and the way it works, so that you can actually map your computations effectively on it, right? So those three concepts are very important, right? And that is also very challenging to optimize for, right? Because not only you need to be aware of these data parallel, SIMD engine, data path or data flow architectures, or the memory hierarchy and data reuse, but there's also multiple use cases, right? Let's say we are talking about computer vision. There could be a use case where you're processing video at 4K at 120 frames per second. That means you have very limited time budget to finish the processing of a 4K image. versus you might be taking a picture and then doing a post-processing on it, which means that there's plenty of time to do the processing. So you can optimize for latency, energy, accuracy, right? So for example, if this is a still image, you take the picture, you process it later, you have plenty of time, so you can optimize for accuracy. But for 4K image, you cannot have extremely high accuracy networks because you have a very limited time budget. So that makes this optimization even more challenging, because there is no, again, single point to optimize for. There's variety of like goals and budgets in terms of your metrics. And yeah, utilizing the hardware architecture is also is not constant, it's not fixed. It's a moving target, because the architecture dimensions, those like features that come with the architecture, they change every generation. There is also multiple types of hardware. And there's these concepts that I mentioned: data reuse, parallelism, data flow architecture to optimize for. So basically the point here is that it is possible to optimize if you're aware of all the metrics and underlying architecture concepts and the budgets, the targets that you have. But doing this manually is very challenging. So we are using AutoML to help us and to do this more systematically, right? So I'll do a deep dive on this one and show you some of our recent work using AutoML for this optimization. So what is AutoML? AutoML is the term that people use for neural architecture search, right? The idea here is that we are optimizing or we are automating the neural network architecture optimization process for a target hardware, right? So this is just a quick overview of main components, right? So let's go through all these like components one by one. One of the important aspects of this search is the search space. So what is search space? Search space is the set of building blocks to construct a complete neural network, right? Actually, I will show even more details about the search space, but it is just a set of like building blocks, such as, do you have convolutions? Do you have certain connections between them? Right? So you have a pool of choices that you can choose from. Right? We'll talk more about this. Trainer is the component where after you have your search space, you sample some choices from there and then put together a neural network. That will be a candidate model. Now you need to evaluate the quality of that model after your choices, right? So now the trainer, there's actually a lot of work optimizing this. Now, if you were to train that candidate model for the task that you're targeting, that will be an extremely slow process to navigate the search space, right? Because training is so slow. There is multiple optimizations in this area. I'm not going to go through all the details, but there's proxy-based, proxyless-based methods. Here, proxy means you're not really training the task itself, but maybe a simpler or faster task, or maybe you're training for only a few epochs, right? Or even there's other techniques where you do one-shot training from a giant network, but let's not go through there, right? But the bottom line here is that you have a trainer that can either train or estimate the quality of that candidate model, right? So that we can sort of understand those choices. And then we have a reward function, right? Multi-objective reward function. So the idea here is that we need to be able to understand the quality of this candidate model after training. And we also need to understand the latency. Here, the latency is the cost that we choose, which means that after picking this candidate model, we analyze it. Maybe we actually run it on the hardware, or we run it on a simulator, or we predict the latency and get the sort of cost of this choice, And the cost here may not be latency all the time. You may actually optimize for energy. You can optimize for maybe you're actually limited with the memory. You can actually optimize for the model size and things like that. Or it could be actually a combination of those. And eventually you generate a reward based on those metrics, and you feed it into this RL controller. Generally, we use reinforcement learning here. But overall, what we're doing is we are picking a choice. We are picking a network, training it, and evaluating it. And then based on the reward, we are learning what choices are better. And then we are picking those candidate models out of this choice pool, right? So this is the overview, right? So I am going to talk about the search space more in our recent work, right? The other components are pretty generic, and they can be reused across maybe different like projects. What I mean is, let's say you're optimizing for GPU, you're optimizing for TPU, you can actually reuse all of the components. But what makes a big difference is the search space. What choices that we're introducing. All right, so in this work that I'm going to present, we focus on a mobile image classification task, right? And we start from like a mobile net, which is pretty popular neural network for mobile use cases to do image classification. We start from the mobile net, and then we introduce some new blocks into our search space so that we can maybe potentially achieve like better neural networks. So one of the key elements, key sort of blocks in the mobile net search space is what they call as the inverted residual bottleneck. In short, we refer to this as an IBN block, and it looks like this, right? These are like tensors, right? So after having this input tensor, what it does is it passes through a pointwise convolution to increase the channel dimension, the Z dimension, right? So X and Y you can imagine as the spatial dimensions, and Z is the channel. So you increase the channel dimension, you apply a depthwise separable convolution, and then you again decrease the channel dimension. This first one is generally called as the expansion convolution. This is the projection convolution. And then if you have the skip residual connection, you add the original tensor back into this projected version, and then you generate the result. Right? This is the main block that the MobileNet used. The key idea behind this is that if you were to do the full convolution, meaning this K by K full regular convolution in this expanded Z, it would have a huge amount of parameters and a lot of like compute. So the optimization here is that we sort of keep the Z small and then increase it using pointwise cheaper convolution, and do this expansive K by K using a depthwise separable convolution, which is a lot cheaper, and then project it back into the original Z. So overall, this block sort of mimics a full K by K convolution done at this expanded Z, but it is much faster. Right? So this is the key block that the MobileNet introduced. So in our work, what we observe is that like MobileNet actually targeted mobile CPUs at the time that they introduced it. But for accelerators, because of the concepts that I talked about, such as the SIMD parallelization and these wide MAC units, it actually has a lot more computation. And what we did is we sort of fused this pointwise expansion with the K by K depthwise convolution, and we achieve a K by K full convolution that is both doing the main kernel application, K by K, but also the expansion, ZI to ZE. So this block, we call it the fused IBN, right? And it turns out that this block could be much more efficient compared to this original IBN, depending on the tensor shapes, right? So I think I have a data on that. Yeah, here. So for example, on this left-hand side, this is the MobileNet IBN, and this is the fused version that we introduced. And then we run this on our TPU accelerator. So we see that on the left-hand side, this runs around like 88 microseconds, only this block. And on the right-hand side, we see that this runs at 60 microseconds. So it's actually faster, but at the same time, this has much more parameters. So this is a win-win situation. You get more trainable parameters. This potentially will increase your neural network quality, but also it runs faster. So this is a great choice that we should pick in our neural network design. But it turns out that this is not universally applicable. Here we do the same transformation, but we observe that the latency is increasing a lot, right? So it's worse, like almost more than 2x worse. And the reason here is that if you like pay attention to the tensor shapes, it turns out that for this shape, it doesn't make sense to do this transformation. So this is the big challenge, and this is where the AutoML helps us. So we introduce these blocks in our search space, and the AutoML picks the choices that make sense for different parts of the neural network. Yeah, here is the demonstration of AutoML designed neural networks. I'm not going to go into all the details, but just by visual inspection, like this is the regular IBN, the conventional IBN, green color. The yellow is the fused one that we introduced. Let's skip the pink one for now, but it's just another alternative, right? So we observe that for different target hardware, such as CPU, TPU, DSP, GPU, AutoML framework picks different choices that are potentially more efficient and different shapes, right? So this is just demonstrating that these blocks that we talked about, like this one versus this one, there's never like a one block that is efficient throughout the network. It is an optimization problem, right? And the search space is huge, so doing this manually is pretty difficult. So yeah, by including that fused block in our search space, and along with the conventional IBNs, we created a neural search space, and then we targeted the edge TPU accelerator for two different types of devices. There's actually the like more PCIe attached, more IoT type of variant of TPU from Coral. In this work, we targeted that one, and there's also a TPU accelerator in Pixel 4 mobile phone. So here we are demonstrating accuracy versus latency. So like towards the left and top is better. So we want to be low latency, high accuracy. Here, like black dots are the existing popular neural networks, and the red one is the one that we designed using AutoML. And we are observing that like optimizing for this target hardware using this more efficient blocks are generating much better neural networks. Same story here, right? So again, like MobileNet V2, V3, and the HTPU variant. It is improving the Pareto frontier, which is the trade-off between accuracy and the latency. Right. So more search space engineering. So this was an effort from I would say 2 years ago, maybe 2 years ago or so, maybe 3 years. So we follow up this work to even improve our search space. The question that we are trying to answer, like how can we have more rich search space that can even have higher utilization and improve that neural networks even better. And for that purpose, we introduce group convolutions into our search space. What is a group convolution? Group convolution is a simple concept where the convolution is not, so normally in a conventional convolution, what you do is you take the entire input channel, you convolve with your filter, and then you generate outputs, and you do it for every input channel by convolving the filters across the entire input channel. Now for group convolution, what you do is you divide it into groups, and then you convolve your filter. Let's say this filter convolves only a portion of the input tensor, right? And that is divided by the number of groups, right? And then you do it for every group, and then you concatenate back the outputs to generate your final output. So it turns out that this group convolution has relatively fewer parameters, and it can be much faster compared to full convolution. And it is more, but it has more trainable parameters compared to a depth-wise separable convolution. So it's kind of like a middle ground between depth-wise and the full convolution. So it is a great tool for AutoML because you can change the group size. You can use it as a knob to configure, right? So if you have more and more groups, then it is less parameters, but potentially less accurate. If you have like wider groups, larger groups, then it has more parameters, potentially more accurate, but more costly as well. And then figuring out the number of groups in certain places of the network is a great task for AutoML. So that's why we introduced this block. And then we use the group convolution in various forms in this IBN that I mentioned, inverted bottleneck block. We introduced group convolution in terms of in place of the depth-wise convolution. We introduced group convolution in place of the fused convolution, right? And then we put this in our search space. Before going into the results, this is just demonstrating how these blocks are enabling like more choices and more sort of rich options to pick from, right? So here we have the fused IBN from the first work. Depth-wise IBN, this is from basically from the MobileNet. These are the ones that we introduced. So it gives us a very nice trade-off possibility, right? So parameters, you can think of them as like trainable parameters. The more you have, the more accuracy that you will get potentially. And blue is the latency. This is the cost. So for example, in this one, if you look at the latency, original fused IBN and depth-wise IBN are the most costly. Like they have a huge cost in terms of latency, but the group versions are running faster. Or on this one, for a different tensor shape, they can be still the fastest option, but they also provide decent number of parameters. So it kind of, the idea is that it just enables a rich search space, right? So that we can optimize. Yeah, so this is the follow-up work that we did for the most recent version of the Pixel phone that has this tensor system on chip, which has our TPU in it. And there is, as a result of that AutoML search, we produced some neural networks that we call MobileNet HTPU v2. The previous one was just MobileNet HTPU. And we compare it to the other like popular networks such as EfficientNet Lite, FBNet, MobileNet v3. We observe that this new search space actually gives us much better trade-offs, and it can increase like the quality of these networks, right? So like, for example, if your budget is, let's say, around like 1 to 1.1 millisecond because of your application, you can actually pick this S variant and then reach almost, you know, somewhere between 77, 78 accuracy. And if you were to do it on a regular existing network such as MobileNet v3, you could only reach 74. Or you may have, like, let's say, an accuracy goal that you want to hit 77. Then you may again pick S and then have it in 1 millisecond. And if you were to do it on the best existing previous neural network, you have to have like much more latency, right? So this is improving that trade-off. So in this work, we didn't stop with the image classification, but we looked into other tasks such as semantic segmentation. This is like image segmentation and object detection as well, not just classification of the objects, but detecting them and segmenting the images, right? I'm not going to go again through all the details, but overall, following this strategy, we are observing the AutoML generated networks are much more efficient in terms of latency and accuracy trade-off compared to existing networks, such as this is using DeepLab v3, which is one of the popular segmentation networks. By following the AutoML search, we can achieve much better quality. Same for the detection. Again, using the same search space, we can improve the quality here. Yeah, we did the same for, actually, we didn't just do the computer vision tasks, but we also did some natural language processing tasks as well. So I skipped the part where about our infrastructure to do this, but one of the like good improvements that we did in that work is that this AutoML infrastructure is kind of independent of the task, right? So as long as you can insert your search space, and as long as you have a way to evaluate your cost of that network on the target architecture, we could search for any task. And that's why we did the natural language processing, which is a lot different than the computer vision. And on this one as well, the red one is the baseline. Actually, this is also another good demonstration of hardware acceleration. So this is running on CPU. You get 470 milliseconds. By just taking it and then running it on TPU, you lower it down to 15 milliseconds, almost real time, right? Depending on your frame rates or your throughput requirements. But then on top of this, when we do the like the neural architecture search, you can actually improve that frontier. For the same exact latency, you can have an increase in your quality, right? Yeah, so I guess that is the result of the AutoML and search and designing the networks. There's actually a lot more opportunities to optimize for the edge AI accelerators. I'm not going to discuss all of those concepts, but one of the very important ones is the quantization and sparsity as well. I just want to mention about the quantization. Even in this chart, we are seeing that quantization in action, right? So this yellow one is for float, blue is for quantized, right? So we can already get good performance improvement, but this can sacrifice some quality, especially for natural language processing. Quantization is not very well tuned, but for computer vision tasks, it's actually very well studied, and we get much better results. Actually, this one is showing much better results. But what is quantization? When we train the neural networks, it is very common to use floating point arithmetic, which uses oftentimes 32 bits per value, right? The quantization basically takes that floating point number ranges and then maps it into a quantized lower bit fixed point arithmetic. This could be 16-bit or 8-bit. And as you could imagine, if we have a quantized network, we still have same number of multiply accumulate operations, same number of model weights, but they are just cheaper, right? So originally 32-bit, now it is, let's say, 8 bits. So this is and on top of it, these edge AI accelerators come with native support for these quantized data types. So we could utilize them much better. And there are multiple ways to do quantization. You could do post-training or quantize. Post-training meaning you complete the training, you froze the weights, you have the network, but you could still pass that network through a quantizer to get a quantized version. But you could also do it during the training as well. Now the result of this is I just want to focus on this chart. This is from our, again, recent work. Floating point versions are the red dots. Quantized version is the blue dot. So you would see that there's actually some slight drop in the accuracy, but overall this is so much better in terms of performance that you would choose the blue dots over red ones unless you want extremely high accuracy, because you get so much reduction in your model size. Right, so this is one of the ways that we can achieve, on top of the hardware acceleration, on top of the neural architecture search, you could do quantization, for example, to even improve that efficiency. So sparsity is another interesting concept, where what we do is we take a fully trained dense network, and we can actually do two things. We can prune synapses, which means the connections between those neural network layers are not completely dense, but it is a sparse connection. We can also drop some of the neurons from the layers as well. So this basically reduces the number of MAC operations. number of parameters in the network. We will have fewer memory accesses, fewer operations to do. Overall, a reduction in the cost of the neural network. Although this may not reflect into your efficiency or performance directly, unless your hardware is capable of running these sparse networks efficiently, which is a challenge for accelerators, because then they have to come with this sort of sparse support. But overall, this is also another like direction to optimize your neural networks, right? So obviously, there is a lot more, but I just want to cover some key ideas and like some details about our work. We can like go through your questions later on, but just wanted to wrap up with some of the future trends for Edge AI that is coming up or already here. Most of this is already here actually, but a few directions if you're interested in this area. One of them is the federated learning and personalized AI. So, so far I've talked about inference, right? So for the edge, we are not really doing training. Like training is done once on the data center, let's say. It's much more compute intensive. You do it once, but then for the train network, you deploy it on the edge devices, you run your inference. That's the most common usage. But there's actually some new type of compute paradigms that is coming up, such as federated learning. The idea here is that imagine this blue dot, like this one is your original network. You deploy it on all the different kinds of edge devices, and then the user, as the users, going through using that network and collecting data, you could actually train the original network and update the network on device. And then this updated network can be published back onto the data center, right? That means, some users may have different types of neural networks that are designed on device now, right? And the task here is that the data center will sort of incorporate those newly trained networks from the on device to come up with one common updated network that can replace the original one. Or the personalized AI is another one where you could specialize the original network based on your usage, right? So there's actually very interesting usages of this for the speech, right? So let's say you're doing like speech recognition on your device. So there's like an original network that is trained for a common speaking patterns and things like that, common voices. But you could actually retrain it on the device and then like tune it for your personal usage. So there's multiple challenges coming with the federated learning. Privacy is one of them, like your data is private. So one of the actual main promises of federated learning is privacy, because we are not sending the data for training to the data center, but we are doing the training locally on the device. We are just publishing the trained network to the data center. So there is a lot of things such as communication of this data, which parts of the model is on the client versus server. And then there's actually a lot of different hardware and data distribution challenges and so on. But don't want to go through all the details. But overall, I would say this is a very interesting direction for future, where the hardware accelerators are not only doing inference, but also on-device training that has certain pretty unique like compute and memory requirements, numeric support, op support. I mentioned, quantization, right? So inference generally happens in a quantized form, but training, doing it in a quantized form is extremely challenging. So these accelerators may have to support full floating point arithmetic to be efficient. A lot of challenges in this direction. Yeah, just wanted to mention about another direction that this is also one of our recent work, where we are trying to optimize the overall sort of ML system, not only the neural network, but the hardware accelerator as well. I think this is like very well in line with the Amir's talk. But what this work is doing is that this is completely changing not only the hardware architecture, but the neural network architecture at the same time, like joint optimization. Right. So again, just wanted to highlight some interesting results from that work. Right. So overall, what we're trying to do is we are trying to maximize the accuracy times the latency times the area. So we have sort of our metric, our goal is accuracy, but we have two costs. One is latency, one is area, as we change the hardware architecture. And the question is, like, if we start from the same area budget from the original accelerator, but we have a task and we have freedom to change the accelerator's architecture, the question is, like, can we do better in terms of the model accuracy and also hardware area from the original, compared to the original design? And in fact, this is showing quite interesting results. Just wanted to focus on this chart. This NAS is the our work's name, and then the sort of greenish dot is the results where it meets the area constraint. So basically, we start from the hardware accelerator area budget, and then we sort of permute or change the like the blocks within that architecture, but still within the same area budget. And then the sort of pinkish dots is the ones where after those changes, the area is larger than the original, so it kind of violates the area constraint. And the blue dot is where the architecture is fixed. The original architecture is fixed. We are just changing the network. So you would see that there's actually a lot of green and pink dots towards the left and like towards the upper region, which means that if we are changing the architecture and the neural network at the same time, there's actually more optimization opportunity. And there is green dots, which means that we can still stay within the same area budget, but still get like better accuracy. Right. So this is very interesting because by doing this joint optimization, we can actually design much better systems compared to what exists today. Right. Yeah. So I just want to wrap up here. Right. So AI on edge devices is here. It's happening. To achieve real-time performance, low latency, low energy, there is hardware accelerators that can bring us there. But what I showed here is that existing machine learning or software solutions may not efficiently utilize these hardware accelerators out of the box. There is plenty of optimizations, AutoML, quantization, sparsity, there's compression work, we could use knowledge distillation, and so on and so forth. I talked about some of these techniques and some of the future directions as well. Yeah, there's actually a lot to do in this area. There's some new use cases coming up, new architecture paradigms. So far, we talked about like tiled processing elements plus scratchpad, SRAM type of memories. Is it the ultimate architecture? Are we done? Probably not. There's actually, I think, more optimizations in this area, and even new design methodologies. ML guided design, exploration, implementation, architecture search. All those concepts are, I think, there to optimize the like ML stack even more. But yeah, that wraps up my talk.